All right, so most of the same announcements as last time. Uh, Proposal due the 13th, short one, two parts basically. Describe your algorithm, so make it clear to me that you understand what the algorithm is, where it comes from, what it does, roughly speaking, and then how you're going to demo it. So I think if you look at the final proposal document, I think I've spec'd it out like a page. So pretty short, still a significant chunk of the grade. This April 13th, that sort of reminds me of something that I didn't put up here, is I've been getting there's several master students in the class that are using this class as part of their portfolio. It's not really that much of an issue if you're not graduating this semester, but if you're graduating this semester, I think advising likes students to try to get all their portfolio stuff done before their last semester, but it still happens. But advising, I think, puts a deadline for they actually want your portfolio to be turned in by the 15th. Now, I swear that in the past, they've, in these rare cases, which they assumed wouldn't happen, but of course they happen a lot. But in these rare cases that they've actually provided a little bit of flexibility on that. But the students from this semester have been saying that advising still wants the portfolios into the 15th. I'm happy to review them as long as you give me 24 hours or at least a business day, so that I can review and make and give my sign off. I have put instructions online on a contributions section that I want you to have like at the very end of it, just like a little paragraph stating what your contributions are because it's a group project. You'll have that in your abstract, I think, or your executive summary of your portfolio, but I want that to be repeated there. But usually it's not much of an issue. But that does mean that you'll have to have something that sort of ticks that box of it at least looks like a solid draft of the report that you'll turn in at the end of the semester as well. So the one at the end of the semester could look identical if you do all your work and then you're just done with your final project. But it's also okay if there's some sheer or some difference between the two of them. So for those that are using it for their master's portfolio in RAS or CS or any of the others that have that as an option, if you're not familiar with this April 15th deadline, then best definitely look into that because most other students in the class will just be submitting their proposals around that time. So it is quite accelerated if you're trying to use this class's project as part of your portfolio, but it's still possible to do. Otherwise, Muddy's Point, concept check, mini project. So, smattering of this Sunday and next Sunday. And then likely, again, because I want to give us the option of skipping Unit 8, if it looks like we're pushing into it, then I've adjusted the drop policies so that these are going to be still available, but optional for that unit. All right, so any questions? A few that are here. If not, then the last time we started talking about bacterial foraging optimization. Stroke eraser tape. Okay. So as we mentioned last time, so there are these bacteria, everything I'm drawn down here. So bacteria like E. coli so there's a bunch of different flagellar schemes that bacteria use. And there are bacteria like E. coli, and let me click this. Be nice if the first time you do this, Zoom would remember and then not prompt you every time. So these bacteria they have flagella for one, so these little hairs that have little motors on them that allow them to rotate clockwise or counterclockwise. And some bacteria have them only at the end. Other bacteria have them all over. And so these are sometimes called paratriculus, I think. Paratrichus, that's right. Paratrichus flagella. So that means they're all over the cell. And so what that means is that when they rotate clockwise, then they unbundle from each other and go in all directions. And that causes the bacteria and the kind of the Reynolds number regime that they swim in, it causes them to kind of stop and just turn to a random angle. But then when they rotate counterclockwise, then you get what's called a flagellar bundle. So all of these flagella sort of flatten out in the same direction and bundle together to become this kind of large sort of propeller device that's in the back. that allows them to move in a relatively straight direction. And then so they can switch between these two just by switching from clockwise to counterclockwise. And that gives us the so-called run and tumble behavior of these types of bacteria, particularly E. coli, but there's plenty of other in this group that have these flagella all over that do this. So this run and tumble bacteria, or what they how they end up using it is that they run for a certain distance, or until they. So if you put them in a medium that has equal nutrient everywhere, they will randomly tumble. So they'll run for certain distances and then at random tumble. So that's where you can kind of come up with this like average run length. But if you put them in something that has a gradient and their nutrients fall off, then they'll run until they hit one of these nutrient fall offs, and then they'll tumble right at that edge. And so they'll go in a random direction and then start running again. And so that is how they individually climb nutrient gradients. But then collectively, they also run and tumble based on the concentration of attractant and repellent signals, other chemicals that are put into the medium by other bacteria. So they both have their private information that seems to be like maximizing a nutrient gradient. They also have public information, which is social information about where the other bacteria are. And bacterial foraging optimization is a model of these two processes to create an intelligent optimization meta heuristic to try to search over spaces in a way that has a dynamism where it can respond to changing nutrient landscapes or changing toxicity landscapes, as we'll talk about. And then it also is very good at global optimization if you give it enough time. So it's less likely to get trapped because of some mechanisms in here that are constantly sort of moving the bacteria around so they can find new global points. So that's the background context kind of from last time. All right, so the social lives of bacteria. So how does this end up looking in a little more quantitative way? So what I've drawn out here is on the y-axis, I've got the concentration of different chemicals. So this green one that I've drawn in, imagine this to be your optimization objective. Just to make everything easy, we're going to make this a minimization problem. And so rather than thinking of this as a nutrient gradient, or not a nutrient gradient, but a nutrient concentration, let's think of it as a toxicity concentration, or, so there's a kind of a toxin gradient that the bacteria alone can follow. So the idea here is just that we're going to try to minimize exposure. So if we have 3 bacteria located here, here, and here, then this one might move downhill on its own. So it's going to try to find this point here. This one might move downhill to find this point here. This one might move downhill to find this point here, just by run and tumbling without any communication or anything like that. So they're minimizers, but by themselves, they might get trapped in these local optima. And ideally, they would all like to be down here, or maybe, we don't know what's happening over here, but maybe it gets the toxin gradient falls off a lot and they like to be over here. But they like to pool their information so that collectively they can find the area that has minimum toxicity. So, like I said, I'm going to call each one of these the positions of our 3 bacteria. So I'm going to call them theta 1, theta 2, and theta 3. You can think of them as candidate solutions. I've drawn this as one-dimensional X, but you could imagine this as a multi-dimensional space, and these are just 3 different positions in the space. So now what we're going to do is sort of model the social lives of these bacteria. And I mentioned that these bacteria have attractants that they leach out into the medium, and they have repellents. And so they themselves have their own attractants and repellents that others sense, but then they're sensing the attractants and repellents of others. And we're going to model that with what I'm calling an attractant kernel, which is basically this little Gaussian kernel, which I'll draw as this little bell curve. So each one of these bacteria, and so what I'm going to do here in a second is I'm just going to copy and paste this on top of these 3. And so each one of these bacteria has got its own little attractant concentration. So it is putting out chemical into the medium that its effect falls off. So there's a certain length scale, which is captured by parameters of this bell curve. So this will go here, this will go here, that will go there, representing how much chemical, how much attractant they individually are putting out, but then also representing how much attractant that they're sensing from others around them. Now, this little bell curve, we are going to end up adding to a cost function with this form here. And this is just basically a normal distribution, a Gaussian. For me, and I don't know for you, maybe this is obvious for everyone else, but at least there's a point, I think it was in grad school, when I looked at the probability density function for a Gaussian, and I realized that it's just an exponential, a negative exponential, a decaying exponential of distance squared from the mean. That's all a normal distribution is. So I went from every time I needed to write down a normal distributions PDF, I always had to look it up because it seemed like it was made out of nowhere. And then once I realized that it's just distance here, and again, maybe this is obvious to you, but at least for me, it was like there's my life before this and my life after this. Is that there's this distance here where here's the position of the bacteria and here's a point, an arbitrary distance away. So this is the distance from the bacteria squared, and then it just gets scaled. So that's the, it gets standardized by some I'm calling width component here. So that scaled or standardized distance, that then just gets into a negative exponential. So we always plot them as bell curves, but really, if we were to plot the squared distance against this, then it would end up being an exponential decay, where this is you're very close and this is your square distance is very far. So bell curves are just exponentials, even though they look humpy. So that's what we're using, this kind of exponential kernel of distance that we're going to place on top of each one of those. So I'll go ahead and do that. So I'm just going to copy this attractant, try to copy this attractant. There we go. And I'll paste it up here. So I'm just going to put this guy on top of this one. And then I'll try to do the same here. What does this button do? Hey, look at that. So I'll put that there, and then this one. All right, so those are the attractants that are being put into the medium by these three coexisting bacteria. So we can see here that some of these bacteria are, this one is putting out a lot of attractants, but it's not feeling really any of the attractants. But this bacteria and these two bacteria have a good chance of feeling each other's mutual attractants. Now, they not only, and these attractants are going to cause them to be more likely to, the next time they tumble, they'll be more likely to tumble toward, I don't want to say it that way, I will say that directions that go toward other bacteria or up the attractant gradient are going to be less likely to cause tumbling, as we'll see here on the next page. But they don't also always or only put attractant out. They also put repellent. And we use the same sort of thing. It's just another little Gaussian kernel or exponential kernel, but we use different parameters. And so we had a height parameter and a width parameter, which, the height parameter just kind of is the normalization here. So, I mean, these aren't probability density functions, so it allows it to be as tall as you want it to be. And the width parameter is how concentrated it is. So we have another one of these where it takes the same shape, but we use possibly a lower width and possibly a different height. So you might imagine that the repellent, you might tune this to be narrower than the attractant. You kind of want the attractant to have a far reach because you want to say that if a bacteria is staying in one particular area and it isn't moving, then that probably means it found a good spot and it wants to bring bacteria from all over. But if other bacteria get close to another bacterium, then you might just not want them to be on the same spot because you want them to kind of search nearby. So the repellent is going to prevent them from collapsing to a single point. but the attractant is going to bring them from all over so that if one finds a really good spot, then they can come to get it. Now, if one happens to just have a strong attractant, but it's not a very good spot, then they're going to average together. So they're going to coalesce in the middle, and that's perfectly fine too. So as we'll see, there's an opportunity in the dynamics of the social system here for bacteria that are in good areas to be stubborn and be anchors that pull the rest into them. And then otherwise, if none of them found a good spot, then they'll sort of coalesce kind of in the same central mass here, but they won't coalesce to the same point because the repellent eventually kicks in and keeps them apart. And there's going to be another process separate from run and tumble that will help ensure that they don't just get stuck in the middle of this landscape. And so we'll get to that here in a second. So I'm just going to complete this picture by copying these little repellent kernels. There. So this guy I'll put here. So this is a separate chemical. So there's three chemicals that the bacteria can all sense simultaneously. The toxin that they want to minimize exposure to, the attractant, which they generally want to be closer to, and the repellent, which they generally want to be farther away from. The attractant and the repellent are signaling chemicals. They don't actually do any physiological damage to the bacteria. They're just there for signaling, for communication. And the toxin, they actually do need to minimize they actually do need to minimize their exposure to. And that's going to be important because we're about to model bacterial death. And bacterial death will only be based on the green curve. It will only be based on the toxicity gradient. Those that accumulate a lot of exposure to high toxicity are going to be purged from the system. That's BFO's version of selection. And so these two do not contribute to the death. They're only there for signaling. So that's the picture that we have here. This is what the space looks like as the bacteria leach chemical into the space. I want to point out, and this will be important when I talk about stigmergy here in a second, or in a couple of slides, but unlike ant colony optimization, this chemical, it moves immediately with the bacteria. It's not an ant colony optimization. An ant goes to a place, she lays a chemical down, she moves somewhere else, the chemical stays there until it decays. That's a key difference. In bacterial foraging optimization, there's still chemicals coupling the bacteria, but they're sort of constantly moving with the bacteria. Now, in real life, that's not how chemicals work, but it's about time scale. And so in ant colony optimization, we're modeling a long-lasting chemical. In bacterial foraging here, it is true that the chemical stays in the medium, but we assume that very quickly it becomes dilute and just kind of goes to max entropy. It kind of goes everywhere and becomes it becomes homogeneous very quickly. So even though in real life, as you move the bacteria around, these two curves aren't going to just move with it. It can be modeled that way because if very quickly, if you put a little bit in and you stop reinforcing it, if it quickly sort of diffuses and then just becomes flat and and homogeneous, then it may as well have just been you just model the reinforced chemical as being moving around, and that's what we're kind of showing here. So you can think of this as chemical being actively emitted by the bacteria. That's why they move around with the bacteria. All right, so hopefully that's enough time to draw that. Any questions about this setup? Okay, great. All right, so numerically here, how do we set this little algorithm up? We've got S number of bacteria. I will generally refer to them as I is the index for each one. So from 1 to S. So that's up here, and then each one again are position theta I. So each bacterium faces a cost function that has two components. So which I'm going to call J and JCC. So J is the boring one. That's our objective we want to minimize. So I wrote it in green because that's the toxicity that we want to minimize exposure to. Then the more exciting one is over here. This is our so-called cell-to-cell cost function. So this is the accumulated signals received from other bacteria. So that's why we've got it as the sum from J to 1 to S, where we're going to sum over the attractants and the repellents from all of the other bacteria. So this first part is our attractant. So because we're minimizing cost, then we're going to make this a negative because like you're attracted to something. So if you're minimizing the cost, then if you're adding an attractant to a cost function, then you have to kind of make it negative. So it's like an attractant is a negative cost. But this is just the kernel that I wrote on the previous slide there. So and so here we see that this is the position of our focal bacteria. This is the position of the bacteria from the sum. And so we look at the distance between the bacteria, and that's how we figure out how much attractant bacteria I is feeling from bacteria J. We're assuming all bacteria have the same kernels, so they all have the same hyperparameter HA and WA. Same thing with the repellent. So no surprises there. Same form. We've got repellent height, repellent width, distance between a focal bacteria and the bacteria from the sum that the nuisance variable we're aggregating out. So that's the repellent concentration from others. That is our cost function that the bacteria are trying to minimize. And they're going to use run and tumble to minimize that. And we're going to go through that algorithm on the next slide here. But the point that I'm just trying to make is that the bacteria are constantly sensing this, and when this goes up, we're going to tumble. And otherwise, when it doesn't go up, we're only going to tumble if we've run for a long amount of time. That's the general gist of this. So we don't have the gradient of this thing. That's not driving it. The closest thing to gradient is we constantly do look at the differences from a recent exposure to the current exposure. And if it goes up or down, then we decide whether to tumble. So key hyperparameters here that you have to set, and there will be more, but is the number of bacteria, the height of the two kernel functions, and the width of the two kernel functions. And that helps determine the kind of desired proximity of the social system. Questions about that? Should just be a mathematical translation of what I had on the previous slide. Okay, so the BFO, there are 3 stages of the BFO, and they all work together. And so up top here, I'm going to say, I just highlight these. We don't know what these are yet. They're going to be defined down here. But there are these additional hyperparameters, which each one of these are a number of times certain things happen. So by default, the termination conditions, because this comes up a lot as termination criteria, in BFO, there's a finite number of runs that you run through, which have to do with kind of different cycles of like how long each bacteria lives, how often they reproduce, those sorts of things. You could come up with a more complex set of termination criteria and allow the BFO to just continuously run. And that's what you want to do if like you're trying to track a slowly moving dynamical objective. But by default, it's eventually just going to run after a finite number, which are going to be determined by these hyperparameters up here, which again, we're going to define in each one of these steps. So look out for those. All right, so first step is chemotaxis. This is the run and tumble that each individual bacteria will do. So how does that work? Whenever we start this step by choosing a random direction. We tumble. How do you tumble? If it helps, all you're going to do here to choose a random direction is you're going to draw, I'll say U from a uniform distribution from -1 to 1. And you could draw that, I'll say I'll draw UK for every dimension. And normalize. So that's one way to choose. That's typically if you're in a complicated multivariate space, how do you choose a random unit vector? You just say, well, if it's a 20-dimensional space, I'm going to draw 20 random numbers between -1 and 1. And then I'm going to take all those random numbers and I'm going to normalize them so that the magnitude of the vector that I get by putting all those numbers together is 1. And then I look at the angle of the resulting unit vector, and that angle will be my random direction. So that's how you draw a random unit vector to move through a multivariate space. So I draw that. And then after I draw that, uncover a little bit here, I run by moving a certain step size in that direction. And so I've got a step size, which for whatever reason in the canonical BFO, the step size you can have different step size for different bacteria. So some bacteria can be faster and other bacteria can be slower. For the purposes of this discussion, we'll just consider step size to be constant. And so you've got a certain step size, which is how much you're going to move in every step of your run. It's kind of your average run length before you reassess. And you'll move in the unit vector direction that you've drawn. And then you're going to evaluate whether your cost function, your J plus JCC cost function, has increased. If it's increased, or you've been doing NS number of steps, then you're going to stop this process. Otherwise, you're going to take another run step. So this stop process, you say, well, shouldn't I tumble? We'll get back to that. It turns out that we're going to repeat chemotaxis over and over. So every time we repeat chemotaxis, it starts with a fresh tumble. So that's why we just end this with a stop. So if cost increases or you've gone a certain number of steps, stop the process. Otherwise, keep running. And then repeat that for a certain NC times. And that's the lifetime of bacteria. So this first step is simulating like all of the chemotactic movement for a single bacterium. And we do that for all of the bacteria. So we're just simulating all these bacteria moving around for their lifetime. But don't worry, these bacteria are going to have an opportunity to reproduce, and this algorithm will have an opportunity to keep going for the different generations of the bacteria. So this is just one generation of the bacterium. That's our chemotaxis. And so this basically models a fine-grained search. So you can think of it as an exploitation rather than exploration. You can think of it at like mutation in the GA, or the simulated annealing maybe at a lower temperature. That's what we're kind of modeling with this step. So we're obviously going to need to add selection to this. So the bacteria that are doing really bad, we need to get rid of them and give them new bacteria an opportunity to come in. And then we're also going to need to do a coarse grain search. So if we got exploitation, then we're going to add selection, like I just said, and then we're going to need to add exploration. So those are the two other steps. The next step on the next slide will be selection. The third step on the slide after that will be coarse grain search or exploration. So any questions about chemotaxis? Okay. So next step, reproduction. So on every bacteria, we're going to calculate its accumulated health. And this is an accumulated fatigue from exposure from this toxin over its lifetime. So we're summing up not the cell-to-cell cost, only the cost from our optimization objective, the thing we want to minimize. And again, we remember that over its lifetime, we accumulate that. After we then sort all of these bacteria, so we see how well they did in their lifetime, how much fatigue did they accumulate in their lifetime, and then we're just going to kill half of them. So the S over 2, remember S are a number of bacteria. Each one of those with the S highest costs just get flushed away, and they get replaced by clones of the others. And by clones of the other, we're actually going to put new bacteria at the positions of the others. And so it's as if each one of those suddenly got access to more resources now that the other ones were dead, and they just duplicate. They just have an asexual reproduction. You just get a clonal reproduction of the bacteria there. So we then repeat chemotaxis and reproduction for a certain number of generations in our generations that you set. So that's why the chemotaxis just runs for the lifetime, sort of one generation. After that generation, you see who survives. You reward the ones that survive by giving them offspring, and you do it all over again, and you do that for a certain number of generations. And that is basically selection. So inspired by selection in the GA. So now all we're left with is exploration. So any questions about this selection operation that goes on in reproduction? Okay, so then third step to BFO, elimination dispersal. So for each bacterium, again, we are going to, with probability, disperse it to a random location. So this is like, the bacteria aren't in a nice laboratory medium. This is like they're out in the wild. There's a bacteria that could, is responsible for the plaque on your teeth. It's in your mouth. You swallow, and fluid flow goes by, and it just gets carried away. It gets dispersed elsewhere. So this is a drift-like process that just moves bacteria randomly to another spot, even if they're doing really, really well where they are. So but that's all you do. And then you repeat chemotaxis, reproduction, and elimination dispersal in ED times. So you've got these hierarchies where you keep repeating things. And then that ends up being the end of the algorithm. So this thing models a coarse-grained search, or we might call it as sort of an exploration. So you have a high mutation rate. That's one way to view that. Or you can view it as drift in the GA, if we're using the GA model of that. If we're thinking about simulated annealing, this is like what happens at high temperatures. Then you just randomly keep moving around the space, regardless of what the fitness is. Either way, this helps give you good dynamic performance with changing objectives, so long as the objectives don't change that fast. So if you did keep this thing running continuously, then if your objective kept changing, then bacteria that get settled in a nice spot, then this thing will constantly keep, even the ones that are doing really well, it will just knock them out and then disperse them to go check out the rest of the space. And so if the space is changing, then if they end up finding a spot that's really good, they'll get anchored there. Their attractant will eventually pull those elsewhere toward them, and then they'll start tracking that. Now, if the space is changing too fast, this is a really slow process, then they'll just kind of end up sort of being stuck at kind of the center of mass of all of these changes. But if it's changing slowly enough, then ED, the elimination dispersal, gives it this dynamic performance. So any questions about elimination dispersal, this sort of drift-like high mutation rate exploration component? Okay, so BFO, that's basically it. So it can be computationally costly and slow. It's a lot to calculate. It's a lot to keep track of. It has good eventual performance finding global minima. So it's a good global optimizer. And so if you have complex multimodal objectives, lots of local minima, it'll kind of gradually explore them all. But because it's constantly sending others out there, then it has a good chance of finding. And because it has this balance of exploration and local exploitation, then it has a good chance of every generation, if it finds a little nook, it'll investigate that nook. And so it's kind of constantly going from far-flung, wide-scale exploration to then a little bit of exploitation and then back and forth. And so it can perform well. It can even do well tracking changes in objectives, at least if the objectives don't change slowly enough. Okay. So that's my kind of summary of BFO. I mentioned earlier that both, ACO and BFO are chemical inspired, but there is a key difference between them. That in ACO, you're kind of leaving these permanent. As your decay rate is slow enough, they're effectively permanent changes in the environment. So in ACO, you actually need to maintain a shared memory, which has its own state that is separate from the state of the individuals. In BFO, the only state you have are the positions of the individuals. And as they move around, you can predict where the chemicals are. In ACO, there's a decoupling where an ant leaves, the history matters. An ant leaves a chemical, the ant leaves, the chemical stays, the chemical then has its own history at that point on. So that is a key difference between these two, even though you might say that they're inspired by similar natural phenomena. And we refer to algorithms like ACO as stigmergic. So this means that, and this idea of stigmergy is often associated with swarm intelligence more broadly. So stigmergy is the indirect coordination through the modification of the environment. So you have these stigmergic shared memories that coordinate individuals instead of direct individual to individual communication. So if you want to figure out, if there was imagine there was a computational problem that had multiple steps that could be worked out on a whiteboard. You can imagine going to the whiteboard and advancing the computational problem. You carry the one or whatever, but then you stop midstream and then you leave out the door and another student comes in. and they need to figure out how can they help with the algorithm. So they look at the board and they say, oh, we're at step 25 in the algorithm. I'm going to do step 26 and 27. They do that, and then they leave, and then someone else comes back. So in this case, they're not directly communicating with each other. They don't even know who they are. They're totally anonymous. They never even saw each other, and yet the work is getting done. That's a modification of the environment that coordinates the work of multiple individuals without any direct individual to individual communication. That is what stigmergy is. ACO directly mimics this by creating a shared memory like that whiteboard. And so that's sort of modeling the physical process where chemicals are long lasting. But the BFO does not attempt that. So BFO doesn't have a shared memory. Its chemicals are immediately responsive to the current position of the bacterium. So we would not call BFO stigmergic, even though it's modeling the effect of chemicals. And we often think of chemical communication when you're putting chemicals out into the environment. We often are, biased to think of that as stigmergic, but it really depends on the lifetime of the chemical. There are ants that puff little volatile chemicals into the air that try to keep other ants nearby, close to them. And that maintains that, so that way they can follow each other. They can constantly smell each other and they follow each other. That's very different than ants that lay chemical trails on the ground that then stay there long after the ant has left. So if the chemical lasts much longer than the agent, is nearby, then it's stigmergic probably, if others are responding to it. If the chemical is really just effectively Wi-Fi in another form, where it only communicates information immediately between two individuals, even though it's instantiated in chemistry, we don't refer to it as stigmergic. So that's kind of what I'm saying here. So PSO is another example that I would not refer to as stigmergic, even though it's bundled into swarm intelligence. So before we then close the swarm intelligence by introducing PSO, I want to make sure, is everybody clear about what I mean by stigmergy? It's just a term that you should know because it's a very popular term when we're talking about swarm intelligence. And might say, where does it come from? And so there was a French researcher who was studying termites and was trying to understand how termites build such elaborate structures. And they noticed that a termite would come and they would leave it'd start building a structure and then it would leave. And then another termite would look at the existing structure and it would adjust its behavior based on what the current structure would look like. Kind of like I was saying, the whiteboard board. And they came up with this stigmergy. And the mergy, the ergy is like ergonomics. It's related to work. And the stigmergy, I think, is it's related to signaling. And so it's this idea where the work becomes the signal. That's where this funny word comes from. So we're not signaling to each other through a separate means, so a separate channel. We're actually using the modification of the environment itself as the coordination mechanism, stigmergy. And we don't actually do a lot of stigmergy in engineering solutions. We probably could, but when you think about multi-robot systems or whatever, we very much lean on the crutch of peer-to-peer communication. How do we implement this in a way where everyone has situational awareness? And rather than using cues from the environment to sort of queue up what is needed from the next individual. Part of the reason we don't do a lot of stigmergy is that if you talk to the distributed algorithms people, like Andrea Richa, for example, it's harder to write proofs for things with shared memory. Shared memory is ugly because it has its own state. It's a lot easier when you just have to keep track of the individuals. But now, if you have to keep track of not only the individuals with their own state, but the state of this world that they all have this combined interaction with, where that world represents a history of interactions with all of those other individuals, it just becomes very difficult to prove, say, convergence, because you have to prove it not only in what's going on at the individual level, but in also they become inextricably coupled through this shared memory. So I would say it's probably easier to build things with these shared memories, but it's very hard to then make performance guarantees about how they're going to work and how the time works. So engineers tend to stray away from doing stigmergic stuff when they have to do verification and validation of their performance. But more experimental engineers, like people in stochastic robotics and engineer, or just generally these more empirical driven designs that are maybe lower stakes, like you're not going to send them to Mars and count on them working without human intervention, then they're willing to experiment with these. But then largely this is a phenomenon that we stray away from because largely engineering is about guarantees. Okay, I've blabbered enough about that. Pretty clear term I definitely want you to know leaving this class. Okay, so that brings us to PSO. PSO, you're going to see, was developed before BFO. It has, and so some of the aspects of BFO were inspired by PSO, or I would say inspired by the things that came before PSO. And so those of you, I think there's at least one who are in Stephanie Forrest's class, saw me talk a little bit about PSO earlier this week. So some of this will be a little bit on repeat. But PSO was dreamed up. Well, I would say PSO gained its strength in the mid 90s because of how well it could train neural networks. So PSO was unveiled at the International Conference on Neural Networks. It was developed because there were not very good ways to train neural networks at the time, and PSO filled a void. So an artificial neural network, quick review, is just this function f of theta, where theta is the parameters we need to change, which takes an input x, outputs an output y, and we tune theta in order to change how y is produced from input x. And so that largely the way we do that training is that we choose these parameters, which we can also call weights, so that this function approximates a data set like this. So I have a data set where I got a first data point x1 that had a certain output y1, another data set x2 that has a certain output y2, and so on. And ideally, if I set theta correctly, theta here, then this function will make it so that if I give it x1, it will then output y1 on its own. And hopefully, if I do this in a good way, that if I give it a value that was not in the training data set, it will give me an output that meets the spirit of the pattern that was in the training data set. So a big problem with training artificial neural networks is this issue of overfitting, where you can match the data set perfectly, but if you give it something that is slightly different from that data set, then you'll get something that is nonsensical in terms of this pattern, but is more an artifact of how things are connected inside the network in order to perfectly encode the pattern inside the network. And so that's why we don't want to necessarily overfit. So then that brings us to, well, how do you do this training? And how do you try to prevent this overfitting? So you set up a loss function that you're going to minimize, like our toxicity, our toxins from our BFO, and it's going to have two parts. And one part will be directly related to getting that data set matched, and that's our mean squared error. There's other error functions you could put here, but generally you're going to try to find some alignment between the outputs that we were given from your training data set and the predicted outputs from the neural network. So you give the input from the data, see what it predicts, compare it to what it should have gotten, take the error, sum up all those errors. That's our mean squared error. That's the thing that we want to minimize. That's the toxin that BFO wants to reduce, and so on and so forth. But we have this overfitting problem. Now, inside the neural network, if there's a particular relationship which is modeled by a certain latent variable inside that neural network, then if there's enough of those, then what the neural network is going to do is it's going to just amplify the weights on those to just overproduce those so that it can perfectly match these training data. So what we would like to do is say, no, what we want you to generalize. And so if all of the degrees of freedom that you have inside you, neural network, all the thousands to hundreds of thousands to millions of parameters inside that F, we want to make all of those parameter weights small so that you distribute your estimation, I'll say mechanics, machinery, across as many different representatives of your network as possible so that your output is generalizing some larger concept rather than your output is just being a direct reflection of the data. And the way that we're going to encourage that is with a regularization term. So this is one of many ways to regularize. And so this, I think, is L2 regularization. So this idea here is that I'm adding an extra cost term that has nothing to do with the data. It has everything to do with the representation. So what I'm saying here is every weight in the neural network, I'm going to take its distance from the origin and try to minimize that. What I mean by that is I'm going to create this tension set up by this parameter, which I can set. So if this parameter is very large, and this will be very important. If this parameter is small, then it might even be ignored and it'll just do the mean squared error. But the idea here is I want to make my weights relatively small. I want to prevent some weights from being super, super large that represent overfitting. So if I try to spread my weights out and bring them close to the origin, make all my weights small, that generally does a better job at preventing overfitting. So that's how regularization works. And so we've got these two things that if we minimize this, hopefully we do a good job training that. And that's our basic kind of background here. So regularization prevents overfitting and stabilizes convergence. Are there questions about that? Okay, great. So this is largely summarizing that. Regularization term encourages small, smooth, centered parameter values that so things like the GA. So at this time, just want to emphasize, and I'm going to probably say this a couple more times formally, there were not very good gradient solvers at that time, gradient-based solvers. SGD didn't exist, Atom, these tools, they didn't exist. The gradient-based solvers at the time did not have things like momentum. They did not have adaptive weights. They just weren't very good at solving these problems. And at that time, people weren't designing neural networks always to be differentiable. So even if you did have gradient-based solvers, you might have a neural network that you'd hit a point where you just couldn't take the derivative, and so you couldn't backpropagate error. So you couldn't use gradient-based solvers. So you could turn to things like the GA, but the GA does not have directional operators. So remember, the GA's got mutation, it's got crossover, selection. None of these things have any sort of direction to them. And so what you end up getting is this a hopping through the space stochastically. So even though we've got this penalization term, this regularization term that is trying to keep the weights near the origin, make them small, the GA will just constantly keep jumping away, and then you have to wait for selection to then wipe those candidates back out. So if you had a gradient-based solver or something that had memory, then it might stay close to the origin, might hug the origin more closely, and then it might then naturally search the space where you want it to search. The GA, it's keep doing, it's like trial and error. So you have to sort of keep waiting for it to violate what you want to say, no, that's a bad solution. I know that it had a low mean squared error, but it also has a really high the weights, there's some weights here that are really, really large. So you're going to have a low fitness, come on back, and then we regenerate. So it ends up being, there's a lot of wasted resources. The GA ends up not being a very good neural network optimizer. So, and like I said, gradient-based optimizers were also poor at that time. Momentum did not exist in gradient-based optimizers. It did exist, but it hadn't been built into neural network training tools, not mature ones at least. What's interesting is now, if those of you who've done, a little bit of work in neural networks, you've probably used Atom as your optimizer, or at least it was available as an option. Atom with momentum is a very good way to train neural networks. And what we'll see in PSO is that if you know how momentum is implemented in Atom on top of the stochastic gradient descent, it looks a lot like the inertia that is implemented inside the PSO. And it turns out that one didn't necessarily influence the other. They both were coming up at roughly the same time. And so there were momentum approaches that were out there, and it just so happened that this idea of inertia was kind of aligned with that. And so you get the same kind of effects out of it. So what we'll see here is that modern optimizers, this momentum allows them to temporarily escape the bounds of this penalty that is coming from the regularizer. So the regularizer is a gravity that is pulling you back to Earth. But occasionally you want to go into orbit. You want to see the final frontier. You want to see space. You want to see what else is out there. You need to explore a little bit. You don't want to jump directly to Mars, but you like to see gradually, well, let's look at the moon first and then Mars. If the moon's looking pretty good, you want at least some opportunity to get up there. You need to achieve escape velocity. And so these directional optimizers, like Atom with momentum, they basically, even though your gradient is pulling you back, they sort of give you some momentum, some to allow you to escape that gravity, at least for a little bit, so that you can explore the space out here in the dangerous overfitting area to see if there might actually be a few solutions that, you know, maybe some of the weights are a little higher than they are down there, but we're still not overfitting and it's allowing us to explore more. So this combination of momentum plus regularization penalties ends up making for very good optimizers or neural networks. And that's effectively what PSO, that's part of the reason why PSO worked so well, is that it effectively added momentum, even though they didn't call it that, they called it inertia. So that's what we're going to get into here. You know, our gradient-based operators today wouldn't even work because a lot of the neural networks back then weren't differentiable. Nowadays, they've come up with lots of really clever ways to do a lot of cool things with differentiable operators inside your neural network. So it's, you know, so it's very different. But that was our background to how it was back when PSO was first came up. So any questions about this background before we set up what PSO looks like? Okay. So particle swarm optimization came out in 1995, International Conference on Neural Networks, Kennedy and Eberhardt. This was a population-based, non-gradient optimizer with inertia. So it, you know, a lot of times when we think about, well, how are you going to get a direction? How are you going to get smooth motion? And it feels like gradients are a way to do that because they establish a gradient direction and then they help you move in that direction. And this is a way that without a gradient, you could still establish these directions. You could kind of build up speed and momentum from your past performance and then keep using that. And then you can also add that regularization to it for similar effects. And so you not only can penalize mean squared error, but you can also do the regularization thing. So it just plugs in really well for training these neural networks. It was inspired by flocking and schooling. So looking at starlings flying and these aggregations where they hold together, turns out that the flock of starlings isn't actually doing anything collectively that is particularly useful. It's not, you know, serving some higher purpose as a blob, but every individual, it actually serves them well to stay close to the other individuals. And then you end up getting this mass that ends up looking very cohesive. And that's in our case here, that's largely what's happening as well, is that we're going to get individuals that are trying to do better in terms of their optimization objective, but they also are going to have some attraction to the others around them. And we're going to add a little bit of pressure for the group to try to do better than the previous group, but it's still largely inspired by the cohesion you see in starlings. And so in the 80s, the computer graphics folks, so there was sort of a very well-known researcher, Craig Reynolds, and came up with some of these first models, computer graphics models of these artificial, you know, herds and flocks and schools, and he called them boids. Boids are like bird-oids, where oid is like. So the invention is like it's a bird-like thing, is a boid. And so these boids, they're very much like BFO in that a boid, you had a bunch of boids, and they kept track of how many boids were very close to them and very far from them. And you could then put parameters in that could say that if, you know, once another boid gets within a certain distance of you, then you have a very strong repulsion from it. If other boids are very far from you, then you have an attraction to them. And by tuning these two parameters and adding a different amount of noise and adding some alignment stuff, then you could get all sorts of different patterns. So you could get patterns that looked like fish schools going around in circles. You could get patterns that looked like starling murmurations that kind of seemed to go everywhere. You could get gnats that sort of didn't really have any large structure, but they stayed close together. So there are all these different patterns you can get just by tweaking these parameters. And Kennedy and Eberhardt said, well, wouldn't it be interesting to simulate human collective motion using these and then put them on kind of a landscape where the human groups have different choices? And let's just see what's going to happen. Are you going to groups that split or whatever? And they were actually surprised to see that in their simulated groups of collective decision makers, that their boids tended to very frequently choose the best options that they gave them. And then that's when they got the idea that, well, maybe we can actually formally make an optimizer that engineers can use to tune neural networks to fill in the gaps that things like GA haven't been able to quite figure out just yet. So that's how it was born. Now, it came out in 95, and at the same year, there's another very famous collective motion model called the VCheck model that especially the condensed matter folks, like the physics folks, when they think about starling flocks or whatever, a lot of their models are built off of the VCheck model. And the VCheck model looks very, very similar, like nearly identical to the particle swarm model. So it's sort of amazing that there wasn't a direct influence between them. And as far as I know, there wasn't. But it showed that people around this time, somebody had the itch of collective motion and they were starting to all model it in the same ways. So it's just kind of fun when you see research that comes out at roughly the same time that looks so similar together. It's very much like Darwin. Darwin and Alfred Russel Wallace pretty much came up with natural selection at the same time. And Wallace adored Darwin and wrote to him and said, hey, Darwin, I've got this great idea. Darwin was a terrible procrastinator. He actually come up with the idea several years beforehand. He just hadn't published it. So let that be a lesson to you about being scooped. And he just tabled it, and and it was sitting there. And when he saw Wallace, he's like, oh crap! And so they wrote the first paper on natural selection together. It's sort of a co-authored thing. But Darwin is largely credited for that. But that was in a case where these two folks who were inspired by the same kind of milieu of whatever was going on at the time, both came up with basically the same idea at roughly the same time. Similar with, I think, what was going on here with VCheck in one discipline and Kennedy and Eberhardt in another. Anyways, so what does PSO look like? So we have N self-propelled particles, SPPs, and they're going to have an inertia, which we'll see how it's modeled in the update formulas. And this is just a tendency to keep moving with that velocity. Then they're going to have an acceleration, which, like in BFO, is going to have these two components. They're not going to have anything that's repulsive, but they're going to have two different attractants, which will somehow sometimes attract them in different directions. So they're going to be attracted to the memory of where they experienced their personal best. They're also going to be attracted to the knowledge, which has to be, we assume that we provide them that knowledge. So this is not a model of what goes on in reality, because this knowledge wouldn't be available in reality. But in our simulated swarms here, we're assuming that every individual knows where the group experienced their best, or where the best individual in the group experienced its best. And that becomes another attractive point. So you're attracted to both of these things simultaneously. There are other versions of the PSO that I used to present in this class, but we don't have to go into more and more iterations of the PSO, but that add additional things. Like there are some versions of the PSO where you create a local best as well. So you have your personal best, there's the group has got its global best, and then there is a small group of individuals that you draw a radius around you and you say, of all of the ones that are close to me, what was your local best? And so, but adding those things adds a lot more computational costs, because now every time you move through it, you have to keep track of who's around me. And then you have to ask each one of them what their personal best is, and then set that to the local best of your group, and then do that again every iteration. And there are data structures that make that calculation faster, to sort of, you only only update things when you absolutely need to update them, so you don't have to do calculations over and over again that you've already done. But still, it adds more complexity, more computation, and it doesn't necessarily improve the performance all that much. But there are elaborations of this. All right, so how do we start this? We initialize them at random positions, and then for every particle, we have an update for their position and their velocity. So we'll start with their position. It's just their current position. This is their current candidate solution, plus their velocity gives them their new position. So this velocity is what we're going to update in this next expression, but current position plus velocity gives new position. This is what gives them momentum. This is going to give this second order effect where changes in velocity take a tick in order to start updating the actual position. So then their velocity gets updated with this formula here, which we'll uncover here. So the idea here is that their velocity is going to be, their next velocity is their current velocity times some weight, which is we're going to refer to as their inertia. So I'll uncover that. So that's the idea that if you have lots of inertia, then your velocity is going to be more important than everything else. And it's going to take a while for everything else to make a much of an effect on where you're going. If you have no inertia, so if you set this equal to 0, then you can turn on a dime. So this is a lot like the mass of an object. It's like F equals ma. That if you sort of reorganize things into this, so that you've got your kind of x dot and your v dot, where v dot is a, then that ma is going to sort of show up here. So it's like the mass of each one of these objects is their inertia. And then the over here we've got the current position of the particle relative to the personal best. So this is, the particle is going to remember where it did the best in terms of the optimization objective, and then the global best over here. And it's going to also know where the point was that the swarm, regardless of who was in the swarm, but where the swarm had its global best, that's what it's going to remember there. Could you wait for your class to start? So then you've got this distance here that is going to get scaled by these terms, which are going to be these learning factors, CP and CG. And so those are hyperparameters which you can set to say how much do you care about your personal best and the group's global best. And then to add a little randomness to move things around, then we're going to have these random factors, which we're just going to draw. Usually, you could draw from 0 to 1. This is uniformly distributed between 0 and 1, uniformly distributed between -1 and 1. Not -1, you could take them in exponential, whatever. It's just easiest to say do it from 0 and 1. And then that will allow you these pressures, which are going to be pulling you back to your personal or pulling you back to your global, then each one of these will, if this one temporarily in this iteration zeroes out, then you'll get pulled to the global one. If this zeroes out, then you'll get pulled very quickly to the personal one, and that adds a lot more variation. So that's the way they've added randomness in here, instead of like adding a noise term like they do in the VCheck model. So, but that's basically the update equation for the PSO. And so there aren't really there's not really any, that's not like in the BFO, there was an update, a motion rule, but then there are these different stages that did all these other things. In the PSO, you just run this, that's it. That's all of the PSO. And so notice that the optimization objective doesn't actually show up explicitly anywhere in the update rule. It shows up by updating the personal best and by updating the global best. So we don't know what the optimization objective is. The actual value of the optimization objective doesn't directly change the movement, but it does update these 2 points, which are attractors for each individual in the group. And that's how this algorithm couples in that information. So questions about this update rule? So it's sort of a much simpler version of what is kind of hinted at in the BFO. Now it was very successful at training ANNs in the 90s. But then loss functions became differentiable, and stochastic gradient descent based solvers. We got adaptive learnings and momentum. Momentum is largely, one of the things that makes this work so well when combined with regularization. So, modern neural networks today, there's a lot better options for it. But still, I use PSO a lot when I do simulation optimization. So still strong for nonlinear and simulation optimization, especially if you've got, non-differentiable um, uh, optimization objectives, or simulation optimization where there's no chance of getting a derivative. It's fast and performs well, but it can get stuck in local optima. So you always have to ask yourself, is my application better suited for GA or PSO? PSO, anywhere you can find a GA that's written, somebody's also written a PSO. MATLAB's got both of them. They're just pre-built in them. There are Python libraries for both. But the GA is still more well known. I have colleagues in computational neuroscience that do a bunch of optimization in just part of their normal workflows, and they'll frequently just do the GA because that's what they know about. And they're doing spiking neural networks and things like that, things that get me back into the sort of like mid 90s stuff where they're actually doing things that SGD just isn't built for. So they're using the GA because they can't use SGD. And I've had several times I've said, hey, if you tried PSO, you can do this. Like, it's a drop-in replacement for the GA. And immediately when they drop in the PSO, they get like orders of magnitude improvement. Like it optimizes faster, they get better solutions. So you just have to kind of know that, like, if you've got a optimization space where you really want to fling things everywhere and see what's out there, then something like the GA is good for that. But if you have, say, I kind of want to do a search around a certain region, I want you to maybe potentially have the option to go elsewhere, but try to keep solutions bound in a particular area. And if you know where that area is, like maybe it's the origin, you had a regularizer, that's great. But if in general, you just kind of are more focused on exploitation of a slightly good option than exploration of all the options, then PSO is much better for that. So it's good to have both of them available. And then based on your application, pick the one that you want. And then, of course, if your speed, if you don't worry about speed, if you got time and you really want to find the global solution, there are other optimizers out there like BFO, which are particularly good at global, particularly good if you have slightly slowly changing objectives, but they're just, they're slow in themselves and they are a little more computationally costly. So that's kind of where we are. So that's all I have to tell you about swarm intelligence. Next unit is on neural networks. So that will, hopefully go down to the fundamentals of neural networks, as well as getting into some of the future of neural networks, into spiking and kind of everything in between is kind of the goal there. So before we close this one out, any questions about these takeaways? Everybody remember what stigmergy is? That will come up. Okay, great. So that's all I've got, the stuff that's due over the weekend, and that's it. So anything comes up, just send me a note. Otherwise, have a good weekend.